Hello, everyone. We're students from CAIS and IBS, and we want to present our work on custom fraud detection in the presence of concept drift. Let us first motivate the problems that we are addressing in our work. Trade traffic is enormous these days. If you look at the statistics provided by World Trade Organization, world trade in goods and services in year 2020 amounted to a total of 22 trillion US dollars. And this is huge. And all these trade traffic is handled by customs. Who are customs? Customs are basically government authorities designated to regulate flow of goods to and from a country and to collect duties levied by a country on imports and exports. And their work is even further burdened by frauds which are frequently emerging in imports and exports. Custom frauds are any fraudulent attempt to reduce the customs duty imposed on goods. Therefore, support for customs officers is needed. Previous works suggested human-in-the-loop inspection format, where fraud detection models provide the most suspicious items for inspection, which are later manually inspected by custom officers, and they confirm if it's a fraud or not. However, past performance is no guarantee of future results. And one of the reasons for that is concept drift phenomena, which happens due to data characteristics and distribution changes over time. In customs, usually it is caused by alterations of importers, goods types, and business partners. So now we arrive at this dilemma because we need to take into account two factors. The first one is catching the known frauds and secure the revenue based on our previous knowledge. But at the same time, we need to acquire new knowledge about the fraudulent behavior, which may change over time. This is formulated as exploration-exploitation dilemma. And there are existing strategies for exploration like batch, random, and bait, and for exploitation like bait, XBB algorithms. But the previous work suggests that hybrid strategy, which is a combination of exploration and exploitation, may perform better and show more robust performance. Therefore, in our work, we're addressing this problem by using a multi-arm bandit problem setting. Here we use many arm bandit to choose the ratio between exploration and exploitation. And if performance of an arm is good, we raise its selection probability. Now let's talk about the experiment settings in more detail. The dataset that we are using is multi-year and million item import declarations from 4 countries. The statistics of the dataset for each country is summarized in the table below, and features which datasets include are these, like items free on board price, gross weight, quantity, and etc. Also, the dataset includes the label of whether a given transaction is fraud or not. So what the goal that we are pursuing is to choose an exploration ratio that maintains the custom selection model in the long run. And the workflow is basically like that. We give a limited amount of annotated training data to initialize the model. And then in each time step, we update the ratio between exploration and exploitation. Then the model selects a batch of items to inspect based on this ratio, which is further manually labeled by custom officers. Then, using this new label data, the model is retrained. To evaluate our method, we define gold standard, or we also refer to it as Oracle, which is basically an optimal strategy which determines the exploration ratio by accessing the whole data set in advance. This setting is unrealistic and it is solely used for the model assessment. The evaluation metrics that we use are these two, norm precision and norm revenue.
Now we'll introduce our method to select the exploration ratio that is named adapt. Adapt takes in the previous ratio decision along with its result and the new week's data stream to produce the exploration ratio for that week. Adapt is the combinations of two signals, model's history performance corresponding to the adaptive performance tuning model and concept drift signals corresponding to the adaptive drift aware strategy. Let's understand how each component works separately before understanding their combinations. For adaptive performance tuning, intuitively, we continue picking the same ratio if its recent results are better than the others. However, for each turn, we can only see the results for only one ratio. Thus, we adopt the setting of reinforcement learning of the multi-arm bandit problem. Each ratio from 0 to 1 with 0.05 difference will be our arm. And the objective is to maximize the precision score over time. We suppose at first each arm receives an equal probability of getting chosen, and then the result obtained in 1 week by the chosen arm will be normalized with respect to the history for any improvements or decrement. The probability for the chosen arm will then be updated, either decreases if the result worsens or increasing if there is improvement. Other arms' probability will be updated following the chosen arms, increasing if the chosen performs badly and vice versa, based on the XP3 algorithms. For ADA, the exploration ratio will be decided on how the new week's data distribution differs from the previous data. More difference requires more exploration. We embed the custom trading data and apply the method of Earth mover distance with normalizations to quantify the concept drift score. The ratio will be based directly on this quantity. Finally, adapt will combine them by first apply ADA to get a candidate for the next arm, and then let APT resample the probability for this arm and a small region of arms around it only. The process is then repeated for the next round.
Then we perform some experiments to evaluate our model. We aim to address these 5 research questions. We want to identify the need for exploration, to check if our model is effective, and we also want to analyze the concept drift in our data, the detection performance on novel frauds, and conduct some ablative analysis. First, let's identify the need of exploration. How much exploration do we need for maintaining a sustainable system? By varying the exploration ratio in the hybrid model, we see that the model performance is highly sensitive to the exploration ratio. In country C, for example, some ratio around 20% perform really well, but some such as 70-80% perform really poorly. Okay. Similar with country C, in country T, some level of exploration is helpful in improving the model performance. 10% to 30% of exploration performs really well and robustly, while full exploitation without any exploration has its performance degraded over time. In country M and N, exploration is not needed, so it really depends on the data and we cannot really say anything in advance. Our model maintains this ratio without any extensive tuning or knowledge about the data. We would like to check if it is still effective in fraud detection. We found that ADAPT performed commensurately compared to the Oracle, which is the best hybrid model. It performs well in both the case exploration is needed, for example, in country C and T, or when exploration is not needed, like in country M and N. So does ADAPT capture the concept drift effectively, and does the concept drift substantially affect the model performance? The concept drift score we used is based on Earth mover distance, and we see that the drift score is quite consistent with the exploration ratio. In country C and T, where exploration is needed, we observe a high level of concept drift. In country C, there is a big jump of concept drift around 2018. If you look at the performance history, indeed, initially full exploitation performed the best, but from 2018, 20% exploration takes the lead, suggesting that concept drift becomes substantial after 2018, and this is correctly captured in our score. We also observed a strong negative correlation between concept drift and model performance, and high concept drift indeed indicates low performance. We also measure the adapt performance among novel traits. We observe that adapt still performs well when novelty occurs. On the set of items declared by new importers, adapt outperform full exploitation strategies. Sometimes exploitation completely fails to pick up frauds with unencountered importers, like you can see in country T, while adapt still perform robustly. So how important is each component of adapt? We see that adapt is generally better than APT and ADA, suggesting that adapt combine really well the performance signal and concept drift signals that is observed in all 4 countries. Here are the full results, with adapt performs the best virtually in every scenarios. That's it. Thank you for listening. And if you have any questions, feel free to contact us.